Algebra 1, Section 11.4, Graphing Square Root Functions. To start, I want to tell you that you're going to need some graph paper. There's graph paper available on my website. You could practice these along with me, and you would still need 8 more for the homework. So whether you do practice it or not, I think you're going to need 2 sheets to be printed from my website to do this full lesson. And also, let me start by actually bringing in a few things from earlier in the year and kind of tie it to what we're going to do today. So not long ago, we were dealing with this right here. This is vertex form of a parabola or vertex form of a quadratic. And you should recall that h comma k is the vertex to the parabola that is formed by whatever we have substituted in there, a completed vertex form equation, a value for a value for h, and a value for k. Okay, without that, let me show you on my calculator. Here I have graphed y equals x squared. Please realize that I guess this is the big main point I want you to realize is that if I type in 1 parenthesis x minus 0 close parenthesis squared plus 0, it looks more like vertex form, but it really is identical to the one above it, right? Because if I take x and I subtract 0 from it, this is still x. You square it, it's still x. You multiply that by, it's x squared. You multiply that by 1, it's still x squared. You add that to 0, it's just x squared. It's just y equals x squared as we have above. Here's the proof of it. When I press graph, you'll see the blue one, and then you'll see the red one graphed right over the top of it. One and then the other, okay? So those are identical. But if I change this, and this is something that you should recall from one of the worksheets in the post-chapter 10 lessons, and I change this to minus 1 and this over here to plus 3. Now, before I even hit graph, think about it for a second. Where do you expect the red graph to be now? The blue one will be in the same place. That's the parent graph. The red one will actually be right 1 up 3. Hopefully you said right 1 up 3. And then again, here's the proof. Parent graph is blue. The red one, if I take the vertex here and I go right 1 up 3, there's the vertex of the red one. And all the other points that are on the blue one would correspond to points on the red one that are right 1 up 3, okay, because that's what the shift is. Okay, now that was something from our past. We're going to be dealing with square roots today. We'll come back to this one in a second. I was showing you some things that were in earlier lessons from the year. Another one very similar to the quadratic would be the absolute value function. Remember that these produce a parabola, something like this, where these that produce an absolute value function, it's like a V shape. It's something like this, right? And sometimes they cross the x-axis and sometimes they don't, okay? But the point is that this has a vertex, this also has a vertex, and in both cases, it's h comma k. We actually saw this very same concept in chapter 6 with point slope form. Now, it's a little bit harder to identify. You should recall that this is point slope form. If not, chapter 6, you might want to review that. And there's 2 things that make this a little bit harder to identify. Number one, they made the decision to use x1, y1 rather than h and k, okay? But either way, they're numbers. They're numbers that would be in here. If this was x minus 3 is equal to 2 for the slope, parenthesis x plus 7, we would know what x1, y1 are, okay? The other thing that makes this look a little bit different than the other ones is that this one is not solved for y. But you know what? That's a really easy fix. Just add y1 to both sides. And then it starts to look very much like the other two. Y equals m parenthesis x minus x1 close parenthesis plus y1. Not to the first power. Y sub 1. Okay, like so. And again, they chose to use x1, y1. They could have just as easily used h comma k as a point on the line. Okay, in these two, it was the vertex. H comma k is the vertex. In this one, it's really just a point on the line. So there are infinitely many lines of this form that you could write for any line because you could substitute any point that's on the line in there. But again, the concept is still there that x comma y is a point on the line. Okay, now all that so that I could show you this. Here's a square root function. Quadratic, absolute value function, line. Here's a different kind. It's called a square root function for obvious reasons. It's got a radical symbol there. That's a square root. And notice how similar it is to the top two especially. A is in the same place. You've got x minus h that's sort of confined to the radical where it was confined to the parentheses here and confined to the absolute value here. You've got plus k that's free of that. And the same deal is going to happen. That h comma k is going to be the shift. The h is going to be the horizontal shift, and the k is going to be the vertical shift. Okay. Now, depending on where you look, and I did look just before I made this video, I looked at a couple of different sources, and some will say it's a vertex, and some will say it's not. If you don't think it's a vertex, well, then it's really just the point where the graph sprouts from, and we'll show you that here as we start to graph them. So maybe it has a vertex, maybe not. I read our book. It does not use the word vertex. So I never could get a definitive answer on that. No big deal, though. Okay, so let's look at some examples. Before we get into graphing, here's just a question about domain. Recall that earlier in the year we also talked about domain and range, domain being all possible inputs and range being all possible outputs. Here they're just asking about the inputs. And I think there's kind of value in seeing this two different ways. So one way to look at this would be to simply say, what values can I plug in for x that would give me real outputs? How far can I go, either to the low side or the high side? I don't want to give that away yet. Before we start square rooting negative numbers, in other words. Okay. Now, a lot of times somebody will say, well, -6. Okay. -6 is where you first run into a problem. Actually, isn't it anything lower than -5? We don't have to deal in integers, but -5 is really the cutoff. -5, if I plug that in here for x, -5 plus 5 is 0. And yes, you can take the square root of 0. Okay. Can you plug in 1, 2, 3? Yes, you can. You can also plug in a half, a third, 3/4, 9/10, 2 and 7/8. All of those numbers would get added to 5, and then yes, you can square root them and come up with a real number. Okay, now I didn't say rational, I said real. Real meaning you didn't square root a negative number. We'll deal more with the non-real numbers in your Algebra 2 class next year. Okay, so really the cutoff is -5, so it's -5 and above. Now, this lesson is full of things that you'll learn more about in Algebra 2. And I'm sorry if I repeat myself on that several times, but it's just true that this lesson is kind of a scratch the surface lesson of many different things that we'll get more in depth in your classes in the future. So what I'm going to show you now is two different ways to display a domain. The way our book likes to do it is to say, okay, hey, tell me what the variable is that you're talking about. Domain is going to be x, all possible inputs. And then use an inequality to say what it can be. So that would be x is greater than or equal to -5. Okay. Now there's also something called interval notation. Pardon me if I did teach you this once. I don't think I did touch on this until just now. But interval notation, it's actually a little bit shorter, is to just say -5 and above would be to say -5, comma, infinity. Okay, and when it's inclusive of the -5, we put a bracket here. Okay, and when it's not including it, like if this were just greater than and not greater than or equal to, it would be a parenthesis. Since infinity can never be reached, we use parenthesis there. Okay, now that's one way to do it. Another way, and this is what you would see if you read your book, is to say, okay, just set this greater than or equal to 0. This radicand needs to be greater than or equal to 0. So just solve this. Okay, and what will you get when you subtract -5 from both sides? You'll get x is greater than or equal to -5. When you subtract 5 from both sides. I'm not sure if I said that right a minute ago. When you subtract 5 from both sides. Okay, so you get what we got here. Let's just use that method on the next one. The 6 doesn't matter, right? Whatever is under here is going to get square rooted and then multiplied by 6. If it's positive after we do the math that's underneath the radical, you're going to be able to square root it. It's still positive. You're going to multiply it by 6. Still positive. Okay. So really all we're concerned with is 4x minus 12. When is that greater than or equal to 0? Add 12 to both sides. Divide by 4. We did not divide by a negative or multiply by a negative, so no reason to change the sign. You've got x is greater than or equal to 3. Okay. Now let's even just test that. Is it okay, because it says or equal to, is it okay to use 3? 3 times 4 is 12. 12 minus 12 is 0. Square root of 0 is 0 times 6 is 0. A 3 as an input would be a 0 as an output. Real number. You can do that. Could I plug in a 3.5? 3.5 times 4 would be 14. 14 minus 12 is 2. Square root of 2 is an irrational number, but it's real. And that number would get multiplied by 6. In fact, that's 6 root 2. 6 times the square root of 2. Pick 4, pick 10, pick 100, pick a million. All of those numbers will work. Pick anything less than 3, and it's going to make the radicand negative, meaning the evaluation of this would be non-real. Okay? So again, to express that, the way our textbook tends to do it with inequality notation, if you will, would be to say x with x greater than or equal to 3 in the brackets. Braces, actually, I think is what that's called. And then 3 and above would be like this, 3 comma infinity with a bracket by the 3. Okay, now let's get into some graphing. Graph y equals the square root of x plus 4. Square root of x plus 4. By translating the graph of y equals the square root of x. So we'll go over to my graph paper. Guess I missed. There. So we'll graph the parent function, that is y equals the square root of x. And I don't think I mentioned that yet, but that is the parent function. Same word as we've used before. And then they said to do this one as well. Okay? Now, here's the deal. Let's do the red one first. When you plug in 0, you're going to square root 0 and you're going to get 0. There's a point right here. When you plug in 1, the square root of 1 is 1. Input 1, output 1. You want to put in a 2 in here? You want to take the square root of 2 on your calculator and try to estimate that? Think of what a better number would be to put here next. Wouldn't 4 be a convenient number to use? So 4 square rooted would be 2. So input 4, the output is 2. Plug in a 4 for x, square root it, your output, your y is equal to 2. The next one would be 9. The next perfect square would be 9. So 9, 3 would be here, okay? And now you may recognize the shape of this as looking a lot like a parabola, and it sure is. It kind of looks like half a parabola tipped on its side. More accurately, what it is it's half of a parabola reflected over the line y equals x. Remember, the line y equals x is like this, and it's a reflection of this portion of the parent graph of the parabola. It's a reflection over that line. And the reason that we don't have the other half of it is, again, the square rooting and negative issue. Okay? Well, first of all, think of it this way. If I pick a value of x that is negative, right? I try to plot, negative 1 comma something. Well, that doesn't work in here because square root of negative 1 is a non-real number. We'll deal with that in chapter 5 of Algebra 2, okay? But also, when I plugged in 1, square root of 1 is 1. It's not two different things, so you're not going to get another point down here, right? That being said, then, this is the whole graph. Don't forget your arrow because that shows that it continues, and it passes the vertical line test. So it is a function. We call these square root functions for that reason. Okay. Now, where is the blue one? Isn't it just going to be 4 units higher? Right? If we just plugged in values 0, 1, 4, 9 here and got outputs of 0, 1, 2, 3, then if I add 4 to each one of those values, that means the y value is just going to be 4 higher. So really, it's just a shift of all these points up 4. And sorry I missed there. I'm doing the best I can. It should pass through that point right there. Missed just a little bit. Best I can do. Okay. Now, truth be told, there is nothing in the world wrong with doing a t-chart here. If you didn't bother with the parent function and you just said, okay, I'm just going to graph that blue one, and 0 would be the number I want to start with, and that output is going to be 4, and then I plug in a 1, and the square root of 1 is 1, plus 4 would be 5, and then I plug in a 4 to give me 2 plus 4, which is 6, and then 9 is going to give me 7, yep, and then you end up plotting the same 4 points. No problem at all. In fact, I think again, there's value in both of those. Okay. Now, the next question, just so that I'm not clicking back and forth as much, the next one is going to be the square root of x plus 3. So let me just back off this, leave the parent function there. And actually, I don't know if I said that right, but it's plus 3, and the square root is extended over the 3. That's going to change things, right? That's going to cause this to be a horizontal shift rather than a vertical shift. If you're thinking of things in terms of h comma k, like I talked about at the beginning, your h comma k here is negative 3 comma 0, right? X plus 3 should be interpreted as x minus negative 3, and that means that we're going to have a shift to the left. Positive here is to be interpreted as minus a negative, which means we're going to have a shift to the left. So negative 3 comma 0. And that being the case, then you're going to have a point here and a point here. And I'm just shifting over 3, right? So there's another one here, and this one over 3 would be like this. They're exactly the same shape. One is just a translation of the other. Okay? Now, the last thing I want to do is just kind of put it all together then. Let me just make sure I got through the examples I wanted to get through. Oh, I wanted to show you that here too. So real quick, there's the parent function. And then if I graph the square root of, which one did we just do? X plus 3. Just proof here. The pink one is 3 units to the left of the black one. Otherwise, they are the same, right? Okay, so yeah, we covered that. I got one more for you then. Let's put it all together and ask you to graph y equals the square root of x plus 5 minus 1. Okay. Now, again, if your method is t-chart, I wouldn't argue with that. I think that's perfectly fine. I would like you to at least recognize that the vertex, if it's called a vertex, so I said I'd mentioned that earlier. If you want to refer to this as a vertex, I know exactly what you're talking about. I haven't confirmed yet that in 16 years of teaching Algebra 1, I haven't confirmed yet that that's actually called a vertex. I found one source that did, and then several sources that never mention it. So anyway, the vertex, I'm doing air quotes with my fingers right now, on this one would be negative 5, negative 1. We should be able to look at that and go, up, negative 5, negative 1. X minus negative 5, and then this is minus 1. So there's going to be a vertex here, okay? And really then it's just a shift of the parent graph of all those points, left 5, down 1. Here I have left 5, down 1. And one more time, it would actually pass right through that point, okay? And then we can graph it. And again, if that's not your favorite method, but you do prefer t-chart, and I think probably some of you would, perfectly fine, but you ought to know at least where to start, negative 5, okay? Now, has it come clear yet as to why it is that? Why negative 5? Oh, it's because this should be interpreted as minus a negative 5. So that's well, that's true. But you know what? The real reason that it is because negative 5 causes the radicand to be 0. I plug this number in first. Negative 5 plus 5, 0. Square root of 0, 0. 0 minus 1 is negative 1. Okay, and then we can go up from there. Try negative 4 because negative 4 plus 5 is 1. 1 is nice and convenient one to square root, right? And you'll get 0, and you're on your way at that point. Okay. Now, one last thing. Go back to here. So this here is known as, well, I don't know if it's known as. Actually, it probably is. It's probably called standard form. Now that I think about it, I'd have to open my book again, and I don't have it open. But maybe it's standard form. I was about to write vertex form. No matter, this is a standardized form for the square root function. And here's the deal. I think this will happen on the very last problem on your homework. that a needs to be outside of the square root for it to be in the form that we can just graph the vertex h comma k. This is the big deal, no matter what you call it. Maybe I shouldn't have put that there. I'll confirm it, and you ask me in the fall, and I'll tell you if I was right or not. That a needs to be outside, and if it's not, if it's y equals the square root of 2x minus 12 plus 3, that's not in this standardized form, and you better just go with a t-chart, right? It has to be exactly in this form. This needs to be, the multiplier needs to be outside. Only x minus h can be inside. It can be plus or minus, and this number can be anything, but there ought not be any multiplier here, okay? To say it another way, 12,3 is not the vertex of this one. Go ahead and graph it on your own if you like to. It's not 12,3. I believe it actually would be 6,3. Okay, that's all I have. Again, make sure you print off some graph paper before you start your assignment. Most of the problems, it's like 8 graphs total. Most of them are going to be graphs. And good luck with that. Bye now.